Good morning, everyone. All right, so today we're working on lesson 6.5, and our topic is problem solving, finding equivalent fractions. Okay, and so our essential question is, how can you use this strategy, make a table to solve problems using equivalent fractions? All right, so Anaya is planning a flower garden. The garden will have no more than 12 equal sections. 3/4 of the garden will have daisies. What other fractions could represent the part of the garden that will have daisies? Okay, so what do I need to find? Blank that could represent the part of the garden that will have daisies. Other fractions that could represent the part of the garden that will have daisies. Okay, and then what information do you need to use to solve this problem? Blank of the garden will have daisies. The garden will not have more than 12 sections. So 3/4 of the garden will have daisies, but the garden will not have more than 12 equal sections. How will you use the information? I can make a table to find equivalent fractions. Okay. Here we could have just said fractions. You didn't need to say other fractions. Fractions that could represent the part of the garden is what I need to find. So solve the problem. So I can make a table and draw models to find equivalent fractions. All right, so 3/4. Okay, so I see a model with 4 sections and 3 of them shaded. Okay, and then I see the same 3/4, but we need to come up with a fraction that's equivalent. So what would happen if we doubled the number of pieces and divided it, instead of 4 pieces, into 8 pieces? So then we would have 6/8, correct? Then is there another way we could divide this? Well, I think we could probably go that way. Each of those are equivalent. And so we have 4, 8, 12 sections, and 3, 6, 9 of them are shaded. So this is no different than what we were doing yesterday. 3/4, if I multiply by 2, I get 6/8. 4 times 2 is 8. 3 times 2 is 6. If I multiply 3/4 by 3, 4 times 3 is 12, and 3 times 3 is 9. Okay, so, and then the models represent that. So what other fractions could represent the part of the garden that will have daisies? And explain. Well, we could say 6/8, right? Because 6/8 is equivalent. And we can also say 9/12. Okay. And basically 6/8 and 9/12 are both equivalent to 3/4. Okay, so let's go on to 254. Two friends are knitting scarves. Each scarf has 3 rectangles, and 2/3 of the rectangles have stripes. If the friends are making 10 scarves, how many rectangles do they need? How many rectangles will have stripes? What do I need to find? How many rectangles Okay. So how many rectangles they need. And I also need to know how many rectangles will have scarves. Not scarves. We'll have stripes. How many scarves will have stripes? What information do you need? Well, each scarf, each scarf has 3 rectangles. Two-thirds of the rectangles have stripes, and they're making 10 scarves. Okay, so how will I use the information? I can make a table. To solve the problem. All right. To find the number of rectangles that have stripes. Okay, so what's our table? We have scarves, right? And we're going to have 1 scarf, 2 scarves, 3, 4, 5, 6, 7, 8, 9, 10. All right, so we have 10 scarves. And now what are the other requirements? What are we doing every time we have 1 scarf? Well, we're going to have number of rectangles with stripes, number of rectangles with stripes over total number of rectangles. Okay, so for 1 scarf, it said 2/3, right? So if we have 2 scarves, that means we have to have 6 total pieces, and 2 times 2 is 4. If we have 3 scarves, 3 times 3 is 9, and 3 times 2 is 6. If I had 4 scarves, there would be 12 total rectangles, and 8 of them would be stripes. So let's see if we start to notice a pattern here. 2, 4, 6, 8. What do you think the next one's going to be? I think it's going to be 10. What's it going to be over? 3, 6, 9, 12, probably over 15. So let's see. 5 times 2 is 10, and 5 times 3 is 15. Yep. So each time we add a scarf, we're increasing by 2/3. So 10 fifteenths, 12 eighteenths, 14 21sts. So the numerator, we're counting by multiples of 2, and the denominator, we're counting by multiples of 3. So 8 times 3 is 24. 8 times 2 is 16. 9 times 3 is 27 total rectangles, and 9 times 2 is 18. And then last, 10 times 3 is 30. 10 times 2 is 20. So does our answer make sense? Well, 20/30ths, that means 2 out of every 3, right? So yes. Let's see, for 1 scarf, 2/3 were stripes. So if I multiply that by 2, I would have 6 total rectangles and 4 would be stripes. So the numerator is increasing by 2's, and the denominator is increasing by 3's. Okay, so I think that makes sense. Alrighty, 255, number 1. So to unlock the problem, remember, use problem-solving math boards if you have them. Scratch paper is great too. Okay, underline the important facts in the problem and choose a strategy you know. So number 1, Keisha is helping to plan a race route for a 10-kilometer charity run. The committee wants to set up the following things along the course. Viewing areas at the end of each half of the course, water stations at the end of each fifth of the course, and distance markers will be at the end of each 10th of the course. Which locations have more than one thing located there? All right, so you remember when we were doing the problems where we wanted to find out where, when two people would wind up being at the same, working at the same time? And we counted the one person like by thirds and the other one by fifths. So we were finding a common multiple for them. Okay, so we're going to do the same thing here. Okay, so there's going to be 2 viewing locations at 1/2 and 2/2. That would be 2 2's is the whole track, right? Okay, and the water stations, there are going to be 5 of them. And so 1/5, then the next one would be at 2/5, then at 3/5, 4/5, and 5/5. Okay, the distance markers, they would show up at 1/10, 2/10, 3/10, 4/10, 5/10, so on, right? 6/10, 7/10, 8/10, 9/10, 10/10. So basically we have to find fractions that are equivalent. Or, yes, where at least 2 of them have equivalent fractions. Okay. So the end, it looks like, would have all 3, right? Okay, and so what else do we have? Okay, so 1/2 is 2 halves. Are there any other halves in this model? Well, half of 5 is 2.5, so none of these would match 1/2. But how about the 10? 2 times 5 is 10, and 5 times 1 is 5. So 5/10 is equal to 1/2. Okay, so let's go ahead and make a list of these. 2 2's is equal to 5/5, which is equal to 10/10. Okay, so we know those. All right, now, how about 1/5? If I multiply 1/5 by 2, I'd get 2/10. So 1/5 equals 2/10. 2/5. If I multiply 2/5 by 2, I'd get 4/5. tenths. All right, so 2/5 is in common to 4/10. 3/5. If I multiply 3/5 by 2, I'd get 6/10. So 3/5 equals 6/10. What happens if I multiply 4/5 by 2? 4 times 2 is 8. 5 times 2 is 10. So I would get 8/10. All right. So we've used them all. The only ones where you're not going to have something is at 1/10 and 3/10 and 7/10 and 9/10. So identify a relationship. Use a common denominator and find equivalent fractions. All right. So that's what we were doing here, where we found equivalent fractions. Identify the locations at which more than one thing will be set up. Circle the locations. Okay, so we did that. Okay, so both the viewing areas all the water stations and the distance markers at 2/10, 4/10, 5/10, 6/10, 8/10, and 10/10 will all have more than one thing. What if distance markers will also be placed at the end of every fourth of the course? Will any of those markers be set up at the same location as another distance marker, or a water station, or a viewing area? So fourths. So if we were doing fourths, it would be 1/4, 2/4, 3/4, 4/4. So none of these first parts are equivalent to 1/4. I can't make 1/4 equal any of the other ones because it's prime. So not 1/4, 2/4. Well, if I multiply 2 by 4, if I multiply 2 by 2, I'd get 4, and 2 times 1 is 2. So 2/4 would be at the viewing area, and it would also be at the distance marker, because 5/10 is also 1/2. So will any of those markers be set at the same location as another distance marker, a water station, or a viewing area? They would also be at viewing area and another distance marker. All right, how about 3/4? 3/4. If I multiply 3/4 by 2, I get 6/8. Well, there's no eighths on my table. If I multiply 3/4 by 3, I'd get 9/12. So no, so the 3/4 doesn't match anything, but 4/4 does, right? 4/4 is equal to 1. So we have, it would be at the viewing area and another distance marker at 2/4, and all three at 4/4. Okay, number 3. 56 students 56 students signed up to volunteer for the race. There were 4 equal groups of students, and each group had a different task. How many students were in each group? Well, that to me is just a straight division problem. We have a total of 56 students, and we have 4 equal groups, right? So, can I share 5 tens into 4 groups? Yes, 1 time each, right? So 4 times 1 is 4. Subtract, we get 1 10 left over. And then we're going to bring down the 6 ones that we already have. So we have 16 ones to share with 4 groups. And I could do that 4 times. So there's going to be 14 students in each group. So there really was no reason to make a table for that problem. Number 4. A baker cut a pie in half. He cut each half into 3 equal pieces, and each piece into 2 equal slices. He sold 6 slices. What fraction of the pie did the baker sell? Wow. So if we have the pie, right? And that's the whole. And then he cut it in half. Okay, so we'll cut it that way, right? And then he took each of the halves and cut, so in half, he cut each half into 3 equal pieces. So like that. Okay. And then he cut each piece into 2 equal slices. So this is a piece here, and he cut it in half, and cut it in half, and cut it in half, cut it in half, cut it in half, cut it in half. All right. And then he sold 6 slices. So let's just show that by coloring in 6. 3, 4, 5, 6. So he sold 6 out of how many? How many are not shaded? 1, 2, 3, 4, 5, 6. So 6 shaded, 6 not shaded. So he didn't sell 6. So he had a total of 12 pieces. So he sold 6/12 or 1/2 of the pie. Right? Half of 12 is 6. Okay, so what did we do? We took the circle, cut it in half. We took each half of that and broke it into 3 equal pieces. We then took all of our 6 pieces and cut those in half. So 6 times 2 was 12. So we had 12 total pieces, and it said he sold 6. So 6/12. Number 5, Andy cut a tuna sandwich and a chicken sandwich into a total of 15 same-size pieces. He cut the tuna sandwich into 9 more pieces than the chicken sandwich. Andy ate 8 pieces of the tuna sandwich. What fraction of the tuna sandwich did he eat? Wow. Well, let's start with what we know. We know there's 15 same-size pieces. He cut the tuna fish sandwich into 9 more pieces than the chicken. Well, if I subtract 9, no, 9 more than the chicken. Okay? So, if it was equal, okay, it would be 7.5, right? So let's just start going 7 plus 8. Okay? So I'm going to say this is the tuna sandwich. So I'm going to put tuna there and chicken here. Okay, this is not true because that's only 1 greater, right? So that's not possible. So how about 9 and 6? Well, that again is 15, but that's only a difference of 3 for the tuna fish sandwich. All right, so let's make it 10 pieces and 5 for the chicken. Oh, that's a difference of 5. So we're close. We're getting there. 11 pieces, 4 pieces. Well, that's a difference of 7. 12 pieces, 3 pieces. That's a difference of 9. Okay, so he ate 8 pieces of the tuna sandwich. What fraction of the tuna sandwich did he eat? So he cut the tuna fish sandwich into 12 pieces. He ate 8 out of the 12. Okay. What is a common factor for 8 and 12? Well, 8 is 1, 2, 4, 8. And 12 is 1, 2, 2 times, 1 times 12, 2 times 6, and 3 times 4. All right. So we have 1 in common, 2 in common, 4 in common. To simplify, we want to divide by the greatest common factor. So 8 divided by 4 is 2. 12 divided by 4 is 3. So 8 twelfths or 2/3 of the sandwich. All right, and number 6. Luke threw balls into these buckets at a carnival. The numbers on the bucket gives the number of points for each throw. What is the least number of throws needed to score exactly 100 points? Well, if we take the largest number, I could do 9 times 10. That would give me 90, and I would need 10 more. And I want the least number of throws. So I can't do another 9 because that would put me at 99, and I can't get 100. So how is there a way of making 100 out of, a 10 out of the remaining 2 buckets? Well, I think if I did 1 times 6, we would now be at 90 plus 6 is 96. And if we did 2 times 2, that would be 100. So I suggest that the least number is 12 throws. Luke threw balls into these buckets at a carnival. The number on the bucket gives the number of points for each throw. What is the least number of throws needed to score exactly 100 points? Okay, so I do want to switch this around though. So 10 throws of 9 gave him 90. One throw of 6 gave him 6, and 2 throws of 2 gave him 4. So not 12, but 13 throws. Ten throws at 9 equals 90. One throw at 6 would be 96, and two throws at 2 would be 96 plus 4, or 100. Okay. So 10 throws at 9, he's at 90. One throw at 6, 90 plus 6 is 96. 2 throws at 2, 96 plus 4, he'd be exactly 100. Okay. So 13 throws. And number 7. Victoria arranges flowers and vases at her restaurant. In each arrangement, 2/3 of the flowers are yellow. What other fractions can represent the part of the flowers that are yellow? Shade the models to show your work. Okay, and so it's saying we're going to go from 2/3 to something twelfths. Well, how did they go from 3 to 12? That has to be multiplied by 4, right? So how can we take the current model, which was broken into thirds, and make it into 12? Well, we just said we have to multiply by 4. So what if we do this? I didn't make it quite even. I should have had these two over a little more to the left. 3, 6, 9, 12. But I do have 12 sections, and I do have 2, 4, 6, 8 shaded. So 8/12. What could be another possibility? What other fractions could I use? Well, this was times 4. Couldn't I just do times 2? Couldn't I say 6? So 4/6. So how could I make 2/3 into 4/6? Well, we said it by multiplying by 2. So cut it in half. Okay, 4/6. Okay, so could have done 3. We could have wound up with 6/9. We could have done 10/15, so on. Okay, so these are just possible answers. Okay, you can have other answers. They just have to be equivalent to 2/3. So that would be 2/3, 4/6, 6/9, 8/12, 10/15, 12/18, and so on. Okay, any of those would have worked. All right, so that's it for lesson 6.5. Our next session will be doing the mid-chapter review for chapter 6. So until then, may the numbers always be in your favor.